Good morning. Today we try to complete this part of the application of neural networks in the as one method in machine learning. We have seen during the last lectures that how what is the concept of machine learning of neural networks and how it works, and also we introduce some math concepts how it works and how the learning can be performed by changing the weights and what criteria that we should follow. So we also introduced the steep descent algorithm as a branch of stochastic gradient. And today, we will go very fast about how to implement the neural networks, like we showed before, how to use it with Octave, and we built some simple function to do that. And also you can do it with Python, and in Python there's some ready-made already algorithms that you can use directly, and with this simple code, it is modified that I found on the internet. So I tried to modify it a little bit, but it is the same that you can use by just uploading this Keras package, and then there's this function. So when you make this sequential, it means that you can put like sequence of layers, and then model add, so you can add layer by layer. So here it means that you have 12 neurons in the input, and the input dimension is 8, and this is the activation function. And as every line that you can add, it means that you add one layer. So it is relatively easy to build neural networks with Python. But now we like to discuss the limitations of backpropagation in neural networks. We studied the backpropagation networks. They have, or the feed-forward neural networks, they have several limitations. One of the limitations that we assume the inputs are independent. For example, if you have this database about, for example, certain electrical network, and then you have, for example, some measurements on the network. So you have voltage at point A, voltage at point B, and current at point A, pressure value at point A, and so on. So you have some values here. If those values are independent to each other, so every row is just collection of measurements, and then we have some output based on those measurements. In that case, in neural networks, feed-forward neural networks works fine because they are independent, and then you can take that every line alone. So they are not like time sequence, or they are not like time series of data. I try to explain this because this is very important concept. Okay, assume that we have those attributes like x1, x2, and xp, for example. Assume that we have a system with 3 attributes, 3 inputs, and then we have certain output y. Okay, so now we have data of x and output y. We try to catch or to capture the relation between inputs, attributes, and the output y. Okay, if this data, let us think about it came from patient, for example, and we have, this is like some data related to health system. So this is, for example, the weight of the patient, the gender, and the blood pressure, for example, and the output is the certain situation. Okay, so now we have patient 1, we have patient 2, we have patient 3, and so on. And there is some hidden relation we try to find. So we can apply regression method, as we have seen, or we can apply the neural networks to find this relation. So because y is some certain function that we don't know in x1, x2, x3, and maybe there's this modeling error here. So now we try to build this relation, and in that sense, regression methods that we saw, or neural networks, the feed-forward neural networks, they are working great, no problem about this. But let us have another situation that those data came from time series. Time series is that y, for example, at a certain time, or the output at time t is equal to x1, maybe it is function, and x1 at t, x2 at t, x3 at t, but it also depends on the history. So it depends on x1 at t minus 1, x2 at t minus 1, maybe x3 at t minus 5, and so on. Now we have time series. So the output depends on the history. The output now is not depending only on the input now. It depends on the input now, but also on the history of the input. So in that case, we have time series. In this case, we cannot apply directly the feed-forward neural networks that we saw before. We need to modify it a little bit to see how it works. If we take a very simple example, that we have only one input, x, and we have one output, y. Okay? Now, if this system that we are looking for, as we saw in the example that we solved with Octave code, using neural networks, we are also using the regression method, that output is, let's say, y equal to exponent of minus 0.2x plus, for example, sine yx plus x. So now, if you look to this, the output depends on what? Only on the input. So one input, it is called memoryless system. Memoryless, why? Because it doesn't have memory about the history. It's just that the current output, y at t, depends only on the input at time t. This is memoryless system. But if yt, let's say it is equal to exponent of minus 0.2 xt, like this one, but plus maybe 5 x at t minus 1, the previous measurement, plus x at t minus 5, or x minus 3. So in that case, the output depends on the current input, but also depends on the previous inputs. Okay? If you try to use the normal regression method that we did, or to use the feed-forward neural networks, the modeling error will be high. The modeling error will be high because you didn't look to the previous. It depends also on the previous. Okay. If we take another example about this, if we want to have like handwritten recognition or optical character recognition. So now, if, for example, and so on. Okay, so I wrote this, and I want my character recognition to understand what I wrote. Of course, first you can divide this like letter by letter. Okay, and then, as I explained before, that we can have like 5 by 5 or 10 by 10 accuracy for every letter. Then we can feed them to the neural networks, like image, character by character. Then we make the learning, and then the system will work in this way. But there is a correlation actually in English language. There's a correlation. So when it is TH, and for example, it is high possibility that it will be, for example, this. So if there is I, then this might be more likely to be S. So there's a correlation. When there is a Q, usually the second letter is U. maybe 95% in English language. So we need to have U after Q. So it is not independent. It is not independent. So if we assume that they are independent, it might work, but the probability of error will be high. Will be higher than if we make more sophisticated network by considering the correlation between those. So there is some history dependence. So when you start to look to this, so we need our network to remember what was the last letter. For example, if the last letter, our network, our neural networks decided that it is a Q, then the next letter, 95%, it will be letter U. So even if U was not clear, for example, if I wrote it in this way, something like that, so it will be able to connect it. So because they know that it is Q, okay? After the Q should be U. So this is high possibility to be the right letter. So this is also another example. So we have actually many examples. This is very, very important example for business people, the stock market. The prices of the stock, for example. If you want to predict, will you invest money in this to buy, for example, shares from a certain company or not? So it is not enough to look to the current only, to the current information. You need, for example, to have also the history or historical data. For example, there are some current important data. For example, for today, what is the price of the share today? Yes, it is important. If there's anything happened today, for example, oil prices, it might affect. But also some historical data. For example, before a couple of days, this company changed the CEO, for example. This might have effect, maybe positive, maybe negative on the prices. So you need also some old data. You need also some old data to be able to predict, like with high accuracy, how will be the prices in the future. So in this case, we need our network also to be able to memorize what is the history. So in that sense, it is not enough to have only the current data, and we need also to have some historical data, or we need to have some memory in our network. Okay, how to do that? After this introduction, we will see how to do that. Either actually, what I'm going to explain for the neural networks, it can be applied also for the regression methods. Okay. Yeah. So one method, or it looks like very intuitive, that we can add memory. We can add memory to our network. How to do that? This very simple way that we can do it. Now, let us start with the simplest case, that we have single input and single output system. And we like to capture the relation between them. So we have here like X, now because it is time series now. It is a time series, so there's a correlation, okay? So this is the first input at, for example, at t equal to 1, at time symbol number 2, 3, and so on. So now we have x1, x2, x3, until xn. And then we have also output y1, y2, y3 until yn. I like now to make the learning for a neural network. So now we have input x and we have output y. This is our neural networks that we like to make the learning for this data. Okay. If you assume that it is only one input and only one output, and this is like time series, there is a correlation between them, the neural networks will not be able to capture the relation. So if you make this, maybe you can try it yourself, that you generate the data like y at time t equal to, let's say, take even simple case, like x at time t plus 3, x at t minus 1, plus 2, x at t minus 2, for example. Okay? So now if you make this time series relation in your code, You write, maybe you can put x as a random number, then you compute what is y, okay, and you generate y. Then you try to make it like xt and yt. Try to make it with the neural networks. It will fail to capture the relation with good accuracy. Okay, how can we solve the problem? Simply, if you add, this is input x, and now this is x, and now I make one delay line, one delay. It means that if this x was xt, then I have second input at xt minus 1. If I added another delay, then I will have here xt minus 2. Okay, so now what I have 3 inputs and 1 output. 3 inputs, it is xt, xt minus 1, and xt minus 2. So it is like moving average. It is called moving, so it is moved. For example, if we put some numbers here to explain how it works, so assume that this one, it gives output 2, this was 3, it gives output 1, this was 5, it gives output minus 1, when it was minus 1, it gives output 0, when it was 7, it gives output like 2, and so on. In the beginning, what you have only single input 1. So I will put, this is in the learning, like table, it would be better. Now, my new neural networks, it has 3 inputs. So I have like xt, and I have xt minus 1, and I have xt minus 2. In the beginning, I have 1 for xt, so it is 1. For those, I put zeros because I don't have any inputs yet. And then the output will be 2. Then, at second situation, xt will be 3. So where 1 will go, 1 will be at the second input. So 1 will be shifted to this, and then I have 0, the output will be 1. Okay? The third input is 5. So 5, 3 will be shifted 1 step, so it will be here, and 1 will be shifted to the other step, so it will be here, and the output is minus 1. And I continue in this way. So now I have a new configuration of my neural networks. So I have 3 inputs and had 1 output. It is the same. You can do it also with regression. For example, if you want to build linear regression, you make it in the same way. You add memory. You add memory for the input. Okay. This looks fine and easy to do. Okay. But for some systems, we might have too many like inputs or the history. For example, in this case, that y equal to, for example, xt minus 3 xt minus 1 plus 5 xt minus 2 plus 7 xt minus 3, and so on. So if this is like a countable number of dependence, this will work fine. This will work fine. If it depends on finite number of history. So for example, here I need four inputs for the history. We might need 5. There is a problem here that we don't know actually how many history points we need. This is unknown because we have only this table, inputs and outputs, and we don't know how many steps in the history that we need. In that case, you can try, of course. You can try with starting with 1-to-1, then you start to take 2 inputs, 3 inputs, 4 inputs, 5 inputs, and increase every time 1 step, and to see how the accuracy will be based on your validation data. So you try it with your validation data, as we will see. If we have more than 1 input, for example, you have x1 and x2 and y, then of course it is the same. So for x1, you put, as it is shown here, the delay lines, and for x2 also you put the delay lines, and for x3 and so on. So in that sense, you can increase your number of inputs and to see if you can get accurate result. Okay. There are some situations where this also will not work. For example, assume you have this system, y at time t equal to 0.5 at y at t minus 1 plus 7 at x at t. Okay. Now in this system we have a recursive equation. So the output at yt depends with 50% on the previous output. okay, and with some on the input now. So in this equation, actually, it might not be enough to use 2 or 3 or 4 inputs because we have a recursive equation now. So it might depend on, actually this one, if you assume that you start with only like xt, let's say equal to 1, and then after that xt is always 0. In that case, y of t, it will be like 0.5 in the beginning, yt, for example, at t equal to 1, yt equal to 0.5, y0 is 0 in the initial condition, so it will be 7 times 1, it will be 7. This will be y1. Then, if x2 and others are zeros, then you will have then y2 equal to 0.5 times 7, then y3 equal to 0.5 times 0.5 times 7, and it will continue like this way, so it will be decaying. It will be decaying until you reach to 0, in the infinity. So it is called infinity impulse response. Infinity impulse response because if you put just 1 here, it will continue up to infinity. But of course, in this case, it is decaying. If this one is greater than 1, it will be divergent, so it will go to infinity. In that case. But it depends on the history. Now, it depends on not finite like this one. This is called finite impulse response. It depends on finite number in the history. But in this case, it depends on the infinity number in the history. Infinity number in the history. So, in some situations, this also, it will have high errors. So, it will not be accurate enough to capture this relation. Okay? I remember one problem that we, during our research here, that we tried to capture the relation between the heart signal and some diseases. So what we have this heart signal, for example, and then, okay, and now we have signals like this is X, is the response of the signal, this one, and then for every signal, we have certain disease that we know. We collected this data. So this heart signal, it has, for example, disease number 1. So we call it like A. This is A. And we have another signal. So the disease was B, and so on. And we tried to build the neural networks to capture the type of the disease. So in that case, the data that we have, they are correlated. So if you take it one by one, it will not work. So we need also to have this recursive input. So the problem here that we have very high accurate data. It means that you know that the heart rate is about 1 per second because we have about 60 or 70 like beat by minute. So we have about 1. So the time here is about 1 second. Okay, so the data rate that we have, it was very high accurate, so it was about 44,000 sample per second. So every 1 beat was represented by 44,000 sample. Okay, when we start to put the delay line with this, like using only 10 inputs, actually 10 inputs would be almost the same data. For example, for 10 inputs will be almost the same data. So that one gives a lot of error, gave a lot of errors. So what we needed to do as one solution, that we need either to change the type of the neural networks, as we will see, another option that we make downsampling. We make downsampling by let's say dividing this by 200 or something like that, in order to have more reasonable type of inputs, but the result, of course, you might lose some important information when you make downsampling. So downsampling is one possible way to have like shorter data, and you have like meaningful inputs. Okay. However, there is another method, very, very important to capture the relation of time series inputs, is it is called recurrent neural networks. Recurrent neural networks. So it is RNN, they call them. So what is the idea of RNN? Simply that you might have like feedback from the input to itself. For example, this is one neural network, or the one neuron. Here they are the weights, but the output of the neuron, it might go back to the same neuron. So in that case, we have recurrency. We try to memorize the states of each neuron. Okay, so in that case, we can build in the memory of the system. So like for example, here the output is connected to the input, and the hidden layer, it might be connected back, and every neuron, it might have its own feedback. Okay, how it works? Okay, we have seen before the single neuron. We have seen the single neuron. We didn't have this like feedback before. But now, with the recurrent neural networks, we might have the inputs as before, but now we have one delay line, and then we have this as an input. So in this case, the output of the neural networks, the output at time, for this neuron at time t is equal to, okay, function of, it will be summation from I equal to 1 up to n. Okay, so it will be wi times xi. This is as before, as we saw before in the neural networks, but now we have a new input. So this is x at t, of course, and this is the weights at time t, and now we have plus w n plus 1 times the output at t minus 1. So now we have, this is the new like recursive function of the output. So it depends on the previous output as well. And now we can adapt for the weights. How to make the adaptation for the weights? It is quite similar to the back propagation, but here we need to make what is called unfolding. Unfolding, it means that now we're looking for every time. So we take it time by time, and we make unfolding for the network, and then we adapt the weights. This is at least one method to adapt the weights and to optimize this network. Of course, in such kind of networks, they are like, or we have more risk for instability because of this feedback. So more careful adaptation we need in that case. Okay, this recursive neural networks can solve the problem of time series. Okay, so now we know that if you are working with machine learning, and you like to capture the relation of a time series, that the history is important. Now you know that you should either use like a delay line for the feed-forward neural networks, or you use recursive neural networks. Okay. However, also the recursive neural networks has a problem. Actually, we have one problem in the neural networks in general, in the adaptation using gradient method. If you remember that the gradient method, it is already here. Yeah. So in the gradient method, the adaptation of the weights depends on the gradient or the differentiation of the function, of the activation function with respect to W. Okay. And this is based on the steepest descent method, if you remember. So if this is our cost function, if it is something like that, okay? So now, if you are here, okay, you can see that as, because the steepest descent method, it gives you the direction where to go, and it depends on the gradient. For example, the partial derivative with respect to W of the function, of the activation function. You can see that as you are closing to some stationary point, this differentiation will approaching zero value. And now if you make this function as a recursive equation, okay, so every W at k plus 1, it depends also the W at k. Okay, and at k plus 2 depends on the w at k plus 1, and k plus 1 depends on w at k, and k depends on k minus 1. So it is like recursion here, or recursive equation, and you can see that the equation will be a multiplication of those gradients. So if the gradient is very small value, epsilon, and then you multiply another time with another gradient, for example, this is at time k, and it is multiplied at time k minus 1, multiplied at time k minus 2, and this will, and that epsilon already is very small value, and very small value multiplied a small value by applied another small value, so you are approaching very fast to 0. What happens when we are approaching 0? There is no adaptation at all. There is no adaptation at all, because this value will be very close to 0. Even the error is large. Even the error, you remember this EK is the difference between the desired output and the actual output. Even the error is large, but when it is multiplied by the gradient and the gradient is small, then we will have very small adaptation for the weights. So the weights will be approaching 0. This behavior is called like vanishing gradient. Vanishing gradient. So the gradient is going or to be closing to 0. In that sense, even the recursive neural networks will be effective to capture that like small history, small time of history, not long history. So it will fail if you are building a system that you wanted to memorize something happens like before, like 1,000 time steps behind. So it will fail. How to solve this problem? We have another network. It's called long short time memory. Long short time memory. I'm not going to go in details here, but all these algorithms are available in packages. So if you go in Python, you will find it already there. So, but before you use it, you should know how it works and what is the purpose of it. So the long short time memory, it can be added, for example, to the hidden layer in the neural networks, and it is widely used in deep learning. The idea here that instead of making this, the output of the recursive neural networks to be depending only on the weights, which means that it will vanish over time. Now we use memory. We add memory. We add memory like this one. So we add memory to the network. So the output will be stored in the memory. So we can keep it as long as we need. We can keep it as long as we need. And in that case, we have, for example, the input. We have the input gate. Where we have the input. So the input gate, if the input is important, we open this, we close this gate, so we can take the input. If the input is not important, so we can open it, or we can decide how much we can have from this input. So it is like wait, but it can be also off. And we have the forget gate. Forget gate is that we decide if we need this memory value anymore, memorized value, or we want to forget it. So if you want to erase it, so you can erase it, or you can keep it as long as you need it. And then the output gate, where we can get the output by this hidden layer. And here we assume that the activation function is tanh function. So this is very simple way how it works. So the main concept here that we add a memory cell. We add a memory cell to our neurons in order to keep the output of the network and keep it stored there. So we can keep it like 1,000 times step and then use it when it is needed. Okay. Deep learning. Everyone, I guess, heard about deep learning. What is deep learning? Or what deep learning means, and what is the difference between deep learning and feed-forward neural networks. One of the problems of neural networks, the feed-forward neural networks, that it depends on the gradient or like stochastic gradient application. And as we explained here, that the learning can be very, very slow when you are close to some stationary point, and if you are like in certain stationary point, for example here, this will be optimum result. For example, if this is local, if this is the global minimum, and this is local minima, one of the local minimas. Okay, maybe we have another here. So now if you are closing to some local minima, and then you will be trapped here. So here the gradient equal to 0. The gradient will be 0 of the function. So we will not have any possibility to update our dates because we stopped here. Even it was bad solution because we have better solution here. This problem becomes more clear as far as we have more layers. So, for example, if you have number of neural networks layers more than 3, then this problem becomes very, very obvious. So it becomes very clear. So when we try to train like 5 layers of neural networks or 7 layers of neural networks by using backpropagation algorithm, and we start making the adaptation, we will stop very fast, and you and your luck. It might be good, it might be bad, but most likely it will be bad because we will have a lot of local minima in the beginning. So it is multidimensional, and then you will stop in first local minima that you have. Because usually when we start learning, we start with random weights. So we initialize the weights of the neural networks with random numbers, and then it will be like stop in the first local minima that you will have. And as you have more and more layers, then you will have more and more local minima. You might have, like for example, if you have 7 or 8 layers, and in every layer you have, let's say, hundreds of neurons, then you might have trillions of local minima. Okay, and maybe there is only one that the global minima, but we don't know it. And most likely, if you want to run your computer for searching for it, it might take like decades in order to find the global minima. This is one very, very important drawback for using feed-forward neural networks. So actually, deep learning is nothing. It is the same as the multi-layer neural networks, like many layers of neural networks, where it can have in every layer many neurons, but in the same time they utilize some different concept for the adaptation of the weights, as we will see them, in order to make this learning much faster and much efficient. Okay, so this is the main concept of the deep learning. The deep learning is many layered neural networks, but they use different procedure for the weight adaptation or for the learning process in order to make the learning fast and efficient. And for example, when we like to use the neural networks to recognize faces, for example, in your iPhone or mobile phone that you want to recognize your face, usually if we increase the accuracy of the face, then we will need like 1 megapixel about, okay? And 1 megapixel, it means that you have 1 million points, and if you want to use neural networks with 1 million inputs, and in every layer we have multiple neurons, so you can imagine how many neurons that we have, how many weight we need to adapt. For example, if we use neural networks where the input we have, let's say, 20 neurons, and in the hidden layer, only 3 layers, and in the hidden layer we use, for example, let's say another 20 neurons, okay, and in the output layer we might have 5 outputs, so we have 5 neurons. If you have like 1,000 inputs, so the number of weights in the input will be 1,000 times 20. So you have 20,000 weights in the input. And in the middle, in the second layer, you have 20 times 20, so you have 400 weights. And the output, you have 5 times 20, so you have 100. Then you can calculate how many weights that you have. If you have 1 million input, like pixels, then you have 10 to the power 6. So you will have 20 million weights in the input layer, and so on. So 20 million weights in the input layer, you need to adapt them maybe thousands of times in order to get the result. So this can be, it will need huge computation resources in order to get good results. Okay. Okay, we will continue after the break. We take 15 minutes break, and then we continue about the deep learning and how it works. Thank you. Hello again. So we continue. I have updated the lecture for today, so you will see in model the latest version of the lecture, and also I added the artificial neural networks function, which can work under Octave or MATLAB, so you can use it. Okay, and also some data has been also added to model, so you can see. And by the way, before I forget, try next lecture to bring your computer with you, because we might have a quiz over model. So try to bring your laptop, just 15 minutes quiz, so it can be over model, or maybe I distribute papers. I have not decided yet, but it is better to bring your computers with you. Of course, I think you can use also your mobile to access model, but okay. Anyhow, why this rectifier linear function is widely used in deep learning? As I said, in deep learning, we have a lot of veneers, a lot of layers, a lot of weights, so we need to do a lot of computations. It is maybe the best way from computation point of view if we have linear network. If we have linear networks, then, as I explained before, we will have convex function, and then we can compute the optimum weights in the way that we showed before in the regression, in linear regression. So it is much easier to find the optimum weights in linear networks than in nonlinear networks. However, unfortunately, linear networks will not be able to capture or to recognize systems if they have nonlinear features. For example, if we like to build some classifier in classification, if the data were not linearly separable, then we cannot use linear separation, linear network. It will not work. It will not work. It will give like large errors. So the model will be bad if we use linear model to classify a nonlinear model or nonlinear data. Okay. The good thing with this rectifier linear unit that it is linear, but it introduces some nonlinearity. So it introduces some nonlinearity that, for example, x, if it is less than 0, the output will be 0. It does not necessarily, of course, to be 0. You can put x anywhere. Okay? So it is 0 if it is less than certain value, and then it is linear within certain range, and also it might have some limit. So maybe it is 1 after some limit. So this kind of function, it introduces some nonlinearity. So, but still it has also some linear portion. In the neural networks, we might start with the instead of starting with random weights, we might start with some initial weights, which is the solution of linear equation. If we assume that it is linear and we compute the weight as a linear problem, and then we start with those weights as initial condition. This can be very effective in reducing the computational time. Here in this example, we built simple example that we have 400 inputs and 1 output, and the data generated randomly with 500 samples, and then I tried to make the learning in the beginning with random initial weights, and in the second I started with the weights which is computed by using linear function, by assuming that it is linear, and I obtained 10 times faster. In the beginning, it takes to learn the network 7.56 seconds, And in the second one, it takes only 0.79 seconds. So you can see that in this simple example, we had 10 times faster computation or faster learning by initialize the network with a weights based on linear function. And we knew from linear regression how to compute the optimum weights in that case. Pattern recognition. Pattern recognition is one of the most important applications of deep learning, or in general in neural networks. Pattern recognition, it can be used to recognize faces, fingerprints, discriminate between items in recycling garbage, for example, voice recognition, handwritten recognition, diagnosis of illness based on images, detecting faults based on time series signal, recognize between civil airplanes and air fighters, an air defense system, and so on. So, I mean, just name it. So we have a lot of applications for like pattern recognition. Okay, and the pattern recognition can be based on one dimension, or 2 dimension, or 3 dimensions, even more. For example, in 2 dimensions, if you have images, then it is 2 dimensions. In signals also, it can be viewed as time and frequency pairs. So we can have also 2 dimensions for time series signals. 3 dimensions, it can be video signals, for example. So we have 2 dimensions as image, but we have a train of images in time, so we have 3 dimensions. And as I said, we might have higher dimensions in that cases. For example, in video, we might have like 3 dimensions, like X and Y, and then time, but also we can have a transformation of the signal, like we have more information about the cosine transform of those images, or we can also have some factors that we can obtain from the image, so we can have more dimensions in that case. Okay. How it works? How can we build some deep learning or machine learning based on the features of the signal? The first thing that we need that to have some feature extraction. Okay, so for example, here we have certain like handwritten text, and then we have feature extraction. Then we apply this feature extracted information to some machine learning, for example, neural networks. Then the meaning of this handwritten is what is your name. So we teach the network that this means what is your name. Then we make the error signal. Then we try to minimize the error as we saw before. But the feature extraction should be also like it should have immunity against, for example, the rotation of the signal. For example, if you rotate it, so it should be the same. For example, here we have the image in this way, but if we have the image in that way, okay, so it is distorted image, and it is also like rotated image, but the feature extraction should have the ability to extract the same concepts from this one in order for the neural networks to know what is the output. Because if you change it and then the outputs change it as well, then the neural networks, even after learning, it will fail to extract the information. So this is important, that to have a reliable feature extraction in order that to be able to extract or to be similar features regardless of the size of the image or the rotation or orientation of the image itself. Or maybe also if you try to learn some like face recognition, then with eye classes or without eye classes, the feature extraction should be able to capture the same person, or at least to have similar features output. If you have beard or without beard, for example, if you have like you cut your hair or something. So always you should be able to recognize the same person. So actually, this challenge is not easy. So before deep learning, they were like developing a lot of feature extraction algorithms in order to have these facilities or these features. In deep learning, we tried to integrate the feature extraction as part of the neural networks. It will not be separated algorithms, and it should be included as well to the neural networks, as we will see how to do it. Okay? But before that, let me explain this simple example about the feature extraction and how to have features of a signal and to be learned to the neural networks. Assume that you want to build a system that is able to recognize the music type. Okay? So now you need, let's say, a couple of seconds or certain period of time to capture the signal. So we have some signal. If you build or if you show or draw the signal of the voice, it can be something like that, of the music. Okay. Now you want to build a neural networks or machine learning algorithm that is able to recognize this music, or and you have already in your database, you have already stored like many music signals, and now by using your mobile phone and just record part of the music, and you want your system to like extract which one it was the right signal. The first thing that we need is to convert this from this time series signal, to some features. So we need to build some features. Okay, so we need here feature extraction. Feature extraction. So we need to build to extract the features of this signal and then compare this feature with the features stored in the database. Okay. What features you can extract from the signal? You can just think maybe some statistical information, maybe the mean of the signal, maybe variance, can be. However, this depends also on the signal strength. So you need to make normalization of the signal, but this might be not enough. So we need also to transform this signal to frequency domain, like by taking fast Fourier transform. Then we will have in the frequency domain the frequencies of this signal. So we have some certain frequencies, like you might get something like that, for example. So of course we have samples. So we might have samples at different frequencies. Okay. And then this is another features that you can extract from the signal. You might think that, okay, I can take image of the signal itself and I consider it as image. This is another possible way. Okay. So always you need, when you have some input, you need first to think what features that I can extract from this signal in order to be able to know how it will work. If you want to build a system to recognize the voice for people, then one possible way, use like filter banks. So we have, this is the signal of voice signal. Then we might have like low pass filter and high pass filter, and then low pass filter and high pass. So every subband is divided like low pass and high pass, and so on. So in that case, we will at the end we might have, let's say, 32 outputs. So I can consider this as features of the signal. Then I can make the learning based on this filter bank and to see what is the output which has the tone of the person. because when we talk, we have the information itself, but we have also the tune. So you know the person from the tune and the way that he's talking. Okay. Yeah. Now, in this pattern recognition, if we talk about image, how to recognize images, then we can use the convolutional neural networks. So the convolutional neural networks, what is the convolution first? The convolution is nothing but filtering. Convolution is filters. So the convolution is the mathematical process of the output of linear system. So when you have linear system and we have input x of t and the output is y of t, what is the relation between x of t and y of t? It is called the convolution. So the y of t is equal to the integration x of lambda h of t minus lambda, and it is the same as xt minus lambda times h of lambda. Of course, you don't need to deep understand what this means, but for those who study system engineering or like control engineering, they know what it means. So it is the relation, because usually systems, they have memory. So this is like the impulse response of the system is h is given by h, and this will be the input. So this will be the output. This is called convolutional integral. Okay, and in discrete form, the convolutional integral is given by this way. This is in one dimension. So if you have the impulse response of system is 1, 0, minus 2, and you have this input, then you can find the output. It will be in this these values. It can be computed in this way. So any linear system, the output of a linear system is like governed or modeled as a convolution between the input and the output. The same will be also in 2 dimensions. If you have 2 dimensions like image, then the output is given by double summation of both dimensions of the image, like in x and y, and then this is the image x, and this is the impulse response of 2-dimensional impulse response. So it is given in this way. So both are identical representation. And if we have, this is the input, 2-dimensional input, and we have this is the impulse response of the system, then this will be the output. I did some simple case. So I took this image myself, and then I read this image by using Octave, and then I make a convolution between this image and certain impulse response. So you can read image by this command, like image read, im_read. So you can do it by like in Octave and also in MATLAB. So I read the image, my photo, and then I use just randomly, I put this h as 0.8, 0.8 minus 1, 0. So this is the filter characteristic, or the impulse response. And then you make the convolution. In MATLAB it is called, or Octave it is called conv2. 2 means 2 dimensions, and this is convolution, 2 dimensions. X is the input with h, and then the output is y. Then I made image show for y, and this was the output. So I put the input in this way. So we have many details here, and then the output was like it gives more like or it shows the borders in the original image. Shows the borders, for example, the border for the streets, because in machine learning or in recognition system, sometimes you don't need to have the full image. You need to extract features, as I said, features of the image. What are the features here? For example, if you want your system to know where is the street, for example, then what you need only the border in the image. So to know where is the street and where is the border, for example. So this image could show what is the borders here. Okay. If you change this value, for example, 0.8, 0.8, if you put another values, then you will have different kind of output image. Every time you change the impulse response, you will have different kind of features. Okay. The idea here in the deep learning, what if we put this feature, the parameters here, let's say we put here W1, W2, W3, W4, and we make this as part of the learning process. So the neural network starts by itself to extract the required features. Okay, we don't start what are features that we give. For example, in this example, we decided the features. We decided that we take the fast-forward transform, and we decided to have that frequency pins to be given to the neural networks. But here we make the neural networks in the loop in order to adapt the parameters or the characteristics of the filter in order to decide what kind of features they will extract from the image. And also in deep learning, usually we make the learning like layer by layer, which make it much more faster. Okay. This exercise, again, you don't need to send it to me, but there's data in model. You can download the data and try to build like using my function in math, or you can use any of those functions and try to find the model of the system. And once you build the model, you can try the testing using data test to check if your model was correctly captured the relation between inputs and output or not. Okay, it's another exercise. Okay, classification. In classification, all what we were talking about is regression. A classification is almost like regression, but instead of having a numeric output, now we have discrete output. If we go to the example in slide 9, that when we talk about the price of cars, so we were sitting, or we were looking to find or to predict the price of the car. But now, if instead of looking to the price of the car, we are interested to know, is the car expensive or fair or cheap? In that case, we have a classification, not a regression, because we have discrete and finite number of classes. In disease, like recognition, also we have classification, like we have disease 1 or disease 2 or disease 3. In face recognition, is this for example, Matti, or this is, for example, Mohammed, then it will be based on, in that case, classification, not regression. So we have a lot of applications in classifications. But still, we can use the same concepts of regression, but in that case, we will have like discrete output. So for example, if we have expensive, fair, and cheap, and now you can see if we made some survey between people and we gave them several cars and we ask them, everyone to say if it is cheap or fair or expensive, then people think differently, and then we have this output. Okay. Now we like to build a model of this data. So it is a classification now, it is not a regression. For example, it is based now on the price and year of manufacturing. Okay, so of course it can be based on many attributes as well. But the output now is discrete. The output is countable output. For example, we have, in this case, we have 3 outputs. We might have 4, 5, 10, 20, but we have discrete number of outputs. Okay, so we have the input x1 and x2 in this example, or we might have more. Then we decide, for example, the output is expensive or fair or cheap, and we can put some labeling like cheap is -1, fair is 0, and expensive is +1. Or you can also put like binary classification. For example, cheap is 001 and fair is 010, and expensive is 100. In this case, you will have 3 outputs. Either you have 3 outputs or 1 output. However, that in the classification, it is preferred to use this like 3 outputs. It can give better result in many situations, when we will talk about Bayesian classifications later. Okay, and now we have, this is the data that we have. So we have X is the inputs. So T here is the samples that we have, and this is the response. R is the response. So for every input, we have a response like expensive or cheap or like fair. Okay, so T is the training samples, like from 1 up to N. Okay. And now what we are looking for, actually we are looking for the best hypothesis that minimize this function. So the expected value of the hypothesis that we use, based on the data, the learning data that we have. Then we have this summation, 1 when the hypothesis of certain input didn't give the same response. What is meaning of 1 here is one function. It gives 1 if this result is true. It gives 0 otherwise. So if the output of this hypothesis was not true, was not the same, then it gives 1. Then we have summation of ones. This gives us the error, the total error or the expected error of using every hypothesis. Our criteria is to find the best hypothesis which belongs to the general hypothesis set to minimize this error. However, it is the same like in regression method. It is not necessarily that the one which gives 0 error is the best in the training. It is not necessarily. You might have one hypothesis gives 0 total error, but because it becomes like memorization, not generalization. So our criteria to test if the hypothesis is good or not, it is by using the validation test. Validation test, not in the training. The good hypothesis that we should have, first, it should be as simple as possible without violating the next condition. It means that we shouldn't have like underfitting or overfitting. Okay? And then achieves the generalization condition with acceptable error. Okay? And 3, it is computation requirement is feasible. So those 3 requirements are very important in order to select the algorithm to apply for certain classification problem. So we should always avoid using NP, non-polynomial complex, because it can have a huge computational requirement for large data size. Okay, linear versus non-linear. So again, those 2 classes are linearly separable, so we can use linear separation like this one to separate between them. So we can say that we are looking for what is A1 and A2 and A0 in order to find the optimum linear classifier in this case. So when Y is greater than 0, then we have a class star, and when Y is less than 0, we have the circle class in this case. So we can build the same way that we did in the regression model, and we can find the optimum parameters here. However, as we will see when we talk about support vector machines, that we need only few points close to the border in order to make this training. But this we will talk about them in different lecture. In many situations, we don't have linearly separable data. So in that case, we may use the same concept by conversion from, or transforming the problem from nonlinear to linear by extending the dimension. For example, in this case, we extend by using, for example, the square of the data, but it's still linear. The classifier is still linear, but we can use nonlinear transformation of the data itself. In that case, we can separate even non-separable data. For example, if we have this kind of data, x1 and x2, so you can see here that we have non-linearly separable. So you will not be able to use any linear separation of this data. But we make transformation. We transform this data by using some algorithm. So instead of using x1, x2, x3, now we have a psi of x1, a psi of x2, and a psi of x3. And in this new dimension, now we go to new space. In this new space, the data is linearly separable. So now we can use linear separation to separate between, or linear classification to separate between data. Okay. As I said, that this topic will be covered in details in different lecture. The learning, the data size is very important, as we explained before. Let us start with this example, this simple example. Okay, now we assume that we have only 2 attributes for certain machine. Okay, so we have a machine, and in this diesel machine, for example, we are measuring, let's say, the vibration and the temperature. So we are measuring the vibration and temperature of this diesel engine, for example. And we assume only binary system, so we try to make it as simple as possible to see the concept of learning. So after this example, you will understand what is the learning mean, what learning means. So now we assume that this engine, it has, we have measurement for this engine, for vibration, we have sensor for vibration, and some sensor for the temperature, temperature and vibration. If the vibration is more than certain value, we set it to 1, and also the temperature. If less than these values, we set them 0. So how many cases that we have? We have either the temperature is normal and the vibration is normal. The temperature is normal, but the vibration is high, so it is 1. So, and the vibration is high, but the temperature is normal, and vibration is high, and the temperature is high. Okay? So this is all cases that we have. Remember, this is the simplest example you can think about. Okay? So in reality, the situation is much more complicated. But now we just we made it as simple as possible. Now, what the hypothesis that you have? You think about hypothesis that you have. The first hypothesis that in all this situation, the engine is, so the output is the engine damaged or not. So in this case, we can start with saying that first hypothesis that all of them, the engine is good. So we don't have problem. What's the second hypothesis that you have? Second hypothesis you have that in this case, when both are normal, then the engine is damaged, but the others, the engine is good. What is the third situation? The third situation is that in this first case, when the temperature is normal, the vibration is normal, the engine is normal. But if the vibration is normal, but the temperature is not normal, then the engine is not normal, and then the others are normal. And you can continue in this case. So we have here like 0, 0, 1, 0, 0, 0, 0, 1. You put all situations. You put all possible situations. Okay? How many situations that we will have? Because we have here 2 of the power. Because we have 2 cases. Okay? So we have 2 of the power 2. Then we have 4. Okay? And then we have, for 4 cases, we have 2 of the power 2 of the power 2. So we have 2 of the power 4. Then we have 16 cases. In this case, it's 16 possible hypotheses. When we talk about hypothesis, we put any possible situation. Any possible situation. So those we have now on the slide from 0, 0, 0, 0 until 1, 1, 1, 1. Okay. You can think the situation if you have 3 cases, then we will have 2 of the power 3 here. So 2 times 2 times 2 is 8. And then the number, it will be 2. So it will be 2 of the power 8. We will have 256. If we have 10, then you have like hundreds of thousands of possible hypotheses. Okay. And remember, still, in this difficult situation, we assume only binary system, either good or not good. Temperature is high or low. We didn't consider in between, which can make the problem much more complicated. Okay. But let us think about this simple case. Now I hope that it is clear what this table means. So 0, 0 means that the temperature is normal, vibration is normal, and then 0, 1, the temperature is normal, the vibration is high, and high for temperature and normal for the vibration, both are high, based on some certain like nominal value. And then those are the hypotheses that we have 16 possible hypotheses. In our learning machine, we try to find what is the best hypothesis represent this problem. Okay, how can we build this? Based on measurement. We need to make measurement. So we look to the history, assume that we look to the history. We found in the history that when the temperature was high and the vibration was normal, we had like damaged engine. So the engine was 1. Okay, now we look. 0, 1, and the image was damaged. Okay, then this in that case we cancel hypothesis 1, because hypothesis 1 is gives 0. We cancel hypothesis 2. We cancel hypothesis 3, we cancel hypothesis 4, and then we take this. We take the possible hypothesis is either 5 or 6 or 7 or 8. Those also are cancelled, and it can be also 13 or 14 or 15 or 16. Then instead of 16 possible hypotheses, by using one measurement, we reduce the possible hypothesis to be 8. Okay? If we have another measurement, then we can also reduce from 8 to 4. If we have another measurement, we reduce from 4 to 2. So as we increase the training data or measurement data, we can reduce the possible size of the hypothesis until we reach to the certain hypothesis. Okay. But in data, when you are looking for the data in your system, you might find another situation where you have 0, 1, like the previous one, but the engine was good, was not damaged. Then in that case we stop, because now we have conflicted measurements. In that case we call this uncertain. We call this situation uncertain, because we have 0, 1. In some measurement it was 0, in other measurement it was 1. Then we cannot rely on this measurement. So we call it uncertain case in this case. But the purpose of this trivial example is to be aware about the training. So it is like another point of view of the importance of training or of learning, that we are reducing the hypothesis space. In the beginning we start with a huge hypothesis space, and using training we try to minimize until we reach to some small certain of possible hypotheses. So this is the supervised learning, that we have the training data is based on some attributes or the factors, and we have responses. Factors and responses. Responses, if the responses are numeric, then we have regression. If the responses are discrete, then we have a classification. Based on this relation, we try to build some model or mathematical model or black box model like neural networks in order to capture the relation, and then we have learned the problem. Always we have uncertainty. So this uncertainty can be represented by this joint probability density function between the input factors and the response. And once we know this probability density function, actually we can build like more sophisticated algorithms. However, it is not always easy to find, and it can be very difficult in many situations. But we will talk about this when in the Bayesian. Actually, next lecture we will start talking about the probabilistic models and Bayesian based classification. So this will be discussed more in the coming lectures. But anyhow, in the learning process, we are always looking for the optimum parameters that minimize the expected value of those parameters based on the training sequence that we have. Once we build this model, we can validate it over the validation set of data. Okay? That's all about the regression part. And next part, we will start next lecture. It is based, of course, because it is Bayesian-based classification or probabilistic models. And I guess maybe many of you, maybe you don't know what is the basic, some concepts about probability theory, and even for those who took some courses maybe a long time ago. So I will start next lecture by revising some concepts in probability theory, and after that we see how to build the probabilistic models and how to use probabilistic models for the classification and also for the regression. This will be part 3 next lecture. And final thing, don't forget to bring your computers for the next lecture. Thank you.